All right, so this from last time then, if we had a quotient of polynomials, we could rewrite it in a form that could be integrated using just algebra, we said, right? Provided the degree of the denominator was bigger than that of the numerator. So that's what we need. And we know from algebra that every polynomial denominator that we need factors uniquely up to reordering those factors as a product of linear factors, ax plus b, and irreducible quadratics, cx squared plus dx plus e. So the result was that every quotient of the form 1, a polynomial divided by a polynomial with the degree of the denominator bigger, right, higher power in the denominator than the numerator, can be rewritten as a sum of other terms this way. This is the partial fractions method, which amounts to reverse putting over a common denominator. Here it is. You can rewrite that quotient as expressions like of this form plus expressions of this form, and all these can be integrated. For each linear factor you see of the denominator, dx plus e, and it depends only on how the denominator factors, not the numerator. The numerator affects what numbers go on top, but only the denominator matters what these things are on the bottom. For every linear factor dx plus e that occurs r times in the denominator when you factor it, you put a number over dx plus e plus a number over dx plus e squared plus finally a number over dx plus e to the rth power, where d and e are just numbers. All these things are just numbers. This is not 2.78 in particular. It's just some number we have to, depends on how it factors. And then for each irreducible quadratic, ax squared plus bx plus c in the denominator that occurs k times, let's say, we need k terms down here. A number times x plus a number over an irreducible quadratic plus a number times x plus a number over the irreducible squared plus all the way down to number times x plus a number over the irreducible quadratic to the s terms if you had an irreducible quadratic to the s power in the original denominator. And then you rewrite this quotient as a sum of these kind of things, and it can always be integrated. That's the big point. Now, if that looks abstract, an example will hopefully clear it up, because that is really abstract. But I want you to be able to do these things in general when you get out of the class, and you'll all be much better at algebra for it, I guarantee. So let's try an example, and then this will hopefully come clear. We did a couple of these last time, the simple cases. This time I want to do a more difficult case, if I can find it here. It's a problem when I have to rush in here. Oh. I think this is it. Yeah, suppose I had to integrate this one now. In fact, I'll repeat a simple example just to remind you. How about that? Suppose I had 1 over x squared minus 3x plus 2. If I have to integrate that, I don't have a technique that applies up to this point. But what can I do? I say, how can I factor the denominator first? Oh, that factors. You can use the method of judicious guessing on a lot of these. Here's how this works. It factors as x plus blank times x plus blank if it factors further. How do I know it factors in terms of real numbers? If I want, I can first check, or I can just guess and hope it works. Right? I look at this expression ax squared plus bx plus c, and I consider b squared minus 4ac. And if that's negative, it won't factor any further using real numbers. Let's see, it's minus 3 squared minus 4 times 1 times 2. Does this look familiar? 9 minus 8 is 1. Ah, that's positive, so it does factor. What's more, because this is a square, it's equal to 1 squared, a whole number squared, I'm actually going to be able to guess what goes in the blanks here. So this factors using real numbers, and these numbers here can be guessed that go in the blanks. And what's more, remember something called the rational zeros theorem or rational roots theorem from algebra? What are the possible numbers that go in the blanks here? What are the possibilities for the blanks when I see x squared minus 3x plus 2 want to factor it? This is the rational zeros theorem. Maybe I should point out that what goes in the blanks are the solutions. I'll just remind you. To the polynomial equals 0. So what goes in these blanks, you put the lead coefficient here 1. That's the 1 here. And then actually, x minus blank and x minus blank is what goes in here. So these are minus the solutions to x squared minus 3x plus 2. And we can solve those with equals 0. And the solutions to the polynomial equals 0 is what goes in the blank. You put lead coefficient times x minus blank, where those blanks are the solutions to this. Well, I can figure this with the quadratic formula if I want, or I can guess what goes in the blanks. I can say these numbers, since the lead coefficient is 1 over here, their sum has to be minus 3 and their product has to be 2. The coefficient's out of here. So what numbers add to minus 3 and their product is 2? Oh, it's minus 2 and minus 1. Or you can solve this with the quadratic formula and you get the solutions x1, x2 are plus 1 and plus 2, and you subtract those in here. So it's x minus the first solution of the quadratic formula times x minus the second, or you can put the two numbers in here with additions here that sum to minus 3 and their product is 2. So either way, we see that this denominator actually factors then as x minus 2, x minus 1, right? If it factors x minus, and if you have trouble guessing those, what you can do is, I started to say, use the rational zeros theorem. The possibilities for the blanks that go in here are plus or minus a factor of the constant term 2 divided by a factor of the lead coefficient 1 up here. That works for every quotient of polynomials. So the only possibilities that could have gone in the blanks are plus or minus 2 or plus or minus 1. That's it, right? Because only the numbers 1 and 2 divide 2 cleanly. So I could try putting all those in, and sure enough, I'd find x minus 2 times x minus 1 works that way. Either way, it doesn't matter. I'll just rewrite this integral as 1 over x minus 2, x minus 1. That's the first step to doing partial fractions is you just rewrite the integral, or the quotient, right? And I gave you at least 3 different ways to do it. You can use the method of judicious guessing, where you write it as x plus blank, and what goes in there, if the lead coefficient is 1, is these two numbers has to sum to minus 3, their product is 2. I hope I'm not repeating too much. Or you can solve by the quadratic formula and take x minus the first number, x minus the last number. Or you can use the rational zeros theorem and say it's a factor of 2 plus or minus over a factor of 1, the constant term and the lead coefficient, and try plugging all those in and see what works. Any one of those 3 methods works just great. All right, whatever your favorite one is. And I find out, in fact, the bottom factors is x minus 2, x minus 1, and the form of the partial fractions depends only on what these factors are. It doesn't depend on what's in the numerator, as long as the degree of the numerator is lower. So this is going to be something over x minus 2 plus something over x minus 1. Guaranteed. That's the partial fractions theorem, if you will. All right. Questions so far? I talked really fast. The part right after this is what we were doing last time. That was the hard. All right. So what goes in there, you use partial fractions. You say it's the method of undoing a common denominator. You write 1 over x minus 2, x minus 1 has this form by the theorem, some number over x minus 2 plus some number over x minus 1. And the way we can find it is by multiplying through by this denominator, x minus 2, x minus 1. If you do that on both sides, so multiply, it says mult, by the denominator, x minus 2, x minus 1, and get equivalently 1 on the left, right, because the denominator gets canceled by that. And on the right, I got x minus 2, x minus 1 times a1 over x minus 2. The x minus 2's cancel, and I get a1 times x minus 1. Then I take x minus 2, x minus 1, multiply it by this term, and the x minus 1's cancel, and I get a2 times x minus 2. So I'm trying to solve for a1 and a2 by taking this expression from partial fractions. This is the partial fractions part here. I'm doing on the side. And now I multiply this out, and subtract over to get 0 on one side is very important. And I'll get something times x plus something. So these are all the x terms, these are all the constant terms. And what I have is I subtract this one over, I get a minus 1 here. And then a times minus 1 is minus a1. I'm sorry, a1 times, yeah, okay, a1 times minus 1 is minus a1 here. And a2 times minus 2 is minus 2a2. And then I've got a1x, so I'll put plus a1x here. a1 multiplying x, and a2x here. So when you multiply this out, you get a1x plus a2x minus a1 minus 2a2 minus 1 all equals 0, just by multiplying this out and grouping like terms. Then we said you can solve for a1 and a2 from that, because what we're saying is this has to hold for all x values except x equals 1 and 2 where it's not defined. How many solutions does this, a number times x plus a number equals 0, have? Only has one solution, right? You subtract this over and divide by this one. Like if this is 3 and this is 2, we said you get minus 2/3 as the solution. So it only has one solution, or you can have no solutions. You put the 0 here and 1 here or something. But in order for this to have solutions for all x on an interval, both coefficients have to be 0, we said, right? That's the only way you can do that. So this is equivalent to saying, this equation holding on an interval is equivalent to saying that a1 plus a2 equals 0. And this one has to equal 0 minus a1 minus 2a2 has to equal 1 to make the second coefficient 0. So both these coefficients have to vanish, we say, have to be 0. Good so far? This is a reminder. Now we can solve these two equations, if I call them equations 1 and equations 2, by substitution, substitute from one into the other, or for bigger systems, it's better to be able to do elimination. I can eliminate a variable by adding a multiple of one equation to another. The result still has to be an equation that's true. If I take equation 1 plus equation 2 here, then the a1s will cancel. Look at that. Or I could take 2 times the first one, add it to the second one, get rid of a2 if I wanted. I'll just add the two equations. a1 plus minus a1 is nothing. a2 plus minus 2a2 is minus a2. And then 0 plus 1 is 1. So evidently, I have that a2 is minus 1. Which says, coincidentally, if I plug that into either equation, let's put it into 1 because it's easier. Equation 1 says a1 plus a2 equals 0. So put into 1 and you find out that a1 is plus 1. Put into 1 and get a1 equals plus 1. Now I've got it. Here's the partial fractions, and I put that into here. a1 is 1. That goes over x minus 2. And a2 is minus 1. That goes over x minus 1, right? And if you get tired of doing that long process, then you can always go to your calculator, we said. I'll put this up here one more time. Let's zoom it in. There we go. Again, the bottom line is the stuff you're typing in. The top line is old stuff I did. I pushed the catalog key. There it is. And I might push a letter on a key with a letter above it here to go to the right section, like I might push, where's F? F, there's a purple F above this key. So I'll push the key with F above it, and it goes to F's in the catalogs, the beginning of the F's. And I do that because I want to be near the expand function, EX. Then I'll use the arrow up here to arrow up to the expand function. There it is, and I'll push enter, and magically it appears at the bottom of the screen. What do I want to expand? The one I want to expand this time is 1 over x squared minus 3x plus 2, so I'll push 1 divided by parentheses, x caret 2 is x squared, minus 3x, and if you put the number first, you don't need the times in there on this calculator, plus 2, close parentheses. So I'm going to expand that quotient, but it needs to know the variable to expand with respect to, so I put comma x, close, and there it is. I'll expand the expression 1 over x squared minus 3x plus 2 in x, push enter, here's what I get back. Pretty print up shows up above it now. It says that when I expand this expression with respect to x, I get 1 over x minus 2 minus 1 over x minus 1. Sure enough, I did this right. So this is faster, and this works online. There are online calculators that can do this for you too. All right. So now, what I've done, zoom this back out, is my original integral, 1 over x squared minus 3x plus 2. I factor the denominator so that I know what the partial fractions and expansion will be. Partial fraction says the integrand can be written in this form, and I solve for a1 and a2 and find out I can rewrite this quotient like this. It's entirely algebraically equal, right? This is the same as this. Just undid the common denominator. Now, see what else I can lose here. There it is. What you can do, the claim is, once you do partial fractions, you can always integrate this by techniques we already have. So I'll rewrite this as integral 1 over x minus 2 with respect to x minus integral 1 over x minus 1 with respect to x. The integral of the difference is the difference of the integrals. And now you can substitute here, let u equal x minus 2. So it's 1 over u instead of 1 over a mess. Then du is the derivative of that dx. Well, it's 1 dx, it's just dx. So I substitute this for u, and I substitute dx for du. Obtaining in this first integral is just 1 over u du in terms of the new variable. That's a good substitution, right? Because I know that first, the integral 1 over u du is natural log absolute value of u, plus a constant that I'll leave off for now. How about the second integral? What do I do? Oh, come on. Put you to sleep already, right? Okay. I let v equal x minus 1, and then dv is the derivative dx is 1 dx. So I substitute that out for dv and this for v, obtaining integral 1 over v dv. All right. Let's look like last time. Integral 1 over v is natural log v. And then there's an arbitrary constant when I drop the last integral. There's my answer. It's natural log, absolute value of u was x minus 2, minus natural log v was x minus 1, plus a constant. That's a good answer. What did we say you can do with some of these? Difference of logarithms is logarithm of a quotient. You guys forget everything this Friday. You had a good weekend. All right. ln x minus 2 over x minus 1. You can rewrite it that way by properties of logarithms. It's a little more compact. So either way is fine with me in the test. All right. There's partial fractions, the basic example. Yeah. Yeah, you can use that. I might ask you to do these by hand, but expand will work on that because this isn't an algebra class, it's a calculus class. Yeah. But as you can see, you can do all this by hand. You don't need the calculator, but it is nice, isn't it? Okay, let's do a more interesting example. Now, suppose I had to integrate x squared over x squared plus 4. How about that? Can I use partial fractions? Answer is it's already in partial fractions form, right? The denominator is already irreducible. How do I know that? B squared minus 4AC is 0 squared minus 4 times 1 times 4 is negative 16 is negative. So this doesn't factor any further over the rails. In fact, if you use complex number, it's x plus 2i times x minus 2i. How about that? So that's not going to, and I can use partial fractions actually to factor it using that, but then you have to integrate with complex numbers, and we don't do that in this class. This is a real class, right? So, what people generally do in these is they don't use complex numbers. They just say, this is irreducible over the reals. How do I rewrite this? And plus, I've got another problem. Why can't, even if it wasn't, even if it was factorable, the numerator has the same degree as the denominator. It's not lower degree on top. You can't apply partial fractions. So what you do when the numerator has at least the degree of the denominator is you first do a long division. You divide the numerator, x squared, by the denominator, x squared plus 4. That's what that means, right? Like, for instance, suppose I was doing numbers. This is analogous to dividing whole numbers. Suppose I want to divide 536 let's say by 40. What would I do to bring that into 536? I said, well, I'll first take the largest power of 10 that goes in there. Looks like, right, 13 times 40. I'm sorry, 10 times 40 makes 400. That's the largest, that's the biggest multiple of 10. 20 times 40 is too big. 10 times 40 is not. So I'll take 40 into 536. 10 times makes 400. And then I'm left with 136. Now 40 goes into 136 3 times. 3 times 40 is 120. And it leaves a remainder of 6. So what does that tell me about the quotient? 536 divided by 40. That tells me then that 536 over 40, when I did the division, had this remainder, and this sum, 13, is the quotient with this divisor and the dividend in there. And so this is equal to, this quotient is equal to the, or this division is equal to the quotient of 13 plus the remainder 6 divided by the divisor 40, which I can then reduce and say it's 13 plus 3/20. All right. So that's long, yeah. Oh, did I botch it? Yeah, I'm sorry, 16. Yes, thank you. 16. And then I've got 8. I've got to reduce that further than 8 is 4 over 10, 2 over 5. All right. Yeah. 13 2/5. Thank you. So that's division with numbers. Now I can do similar division with polynomials, right? I'll divide x plus 4 into x squared, and I'll say, how many times does x squared go into x squared? Oh, it goes 1 time. And then 1 times x squared plus 4 comes down here. And just like over here, I subtract down. I take x squared minus x squared is 0. 0 minus 4 is negative 4. And I say, oh, that's the remainder. This is the quotient. And so I know that x squared over x squared plus 4 can be rewritten as the quotient, just like I did here, quotient plus the remainder over the divisor. Right? The quotient was 1 plus the remainder of minus 4 over the divisor x squared plus 4. How about that? Now I know what to do with this. I'll just take this integral when the numerator is at least as high a power as the denominator and rewrite it after this division as equivalently as 1 minus 4 over x squared plus 4. All right? So there it is. It's just algebra again. I take this quotient, rewrite it like that, and now partial fractions applies to this, but I don't need it because it's already in partial fractions form. We saw that up here. Already in partial fractions form because it's an irreducible quadratic in the denominator, irreducible second degree polynomial. So I just integrate it, and the claim is I can integrate at this point. How can I integrate that? Integral of 1 is easy, it's x. I might say minus 4 times integral 1 over x squared plus 2 squared to write it suggestively. Where have we seen that before? How can I do that? I could think that is square root of x squared plus 2 squared. You did the homework, right? Squared, x squared plus 2 squared squared. So there is an x square root of x squared plus 2 squared in there. I could substitute x equals a tangent theta is 2 tangent theta. And this will work, dx being then 2 secant squared theta d theta, and it will be an integral we can do with the triangle. And then we said also sometimes it's useful to memorize this thing. 1 over x squared plus a squared actually has a formula that I kind of like to memorize. This one isn't too bad. It's 1 over a. So, or you can memorize the formula 1 over x squared plus a squared is 1 over a arctangent x over a plus a constant, right? So I could rewrite this as 1 over 2 arctangent x over 2 plus a constant. And now we see that this integral actually comes out to be x minus 2, arctangent 1/2 x plus c. Okay. Well, I hear the yawns already, so I got to wake you up for something. So one of the fun things about this class is there's a lot of interesting history with these things. And this one has some interesting results. What is the problem with this method? We said all you have to be able to do is factor the denominator, and this always works. So how can it ever fail? What's more, the denominator always factors like that into irreducible quadratics and linear factors. Knowing that, how can this method ever fail? And if the degree of the numerator is higher, I can always divide and do this. So now I should be able to do the quotient of any polynomials, even if the degree of the top is higher, or the same power or higher. It's missing this little subtlety here. I'll ask, how am I going to be able to factor it? It may be that you can't factor it exactly. All hope is not lost, I'd like to tell people, because modern computers can factor these things pretty accurately, as accurately as you want, but they won't get exact things in terms of roots and that sort of thing. Is the trouble. Let me put this on the computer here. And we'll do a story, maybe we'll wake up. There's a famous theorem called Abel's impossibility theorem that states there is no solution in radicals, meaning roots, to general polynomial equations of degree 5 or higher, and hence you can't factor them degree 5 or higher either with a general formula. We just showed last time, right, that you can always factor a second degree polynomial, ax squared plus bx plus c, or if it's reducible, using the quadratic formula, right? It's lead coefficient x minus the first solution, x minus the second. There's also a cubic formula. If I have an ax cubed plus bx squared plus cx plus d equals 0, you can solve that and then find the things that goes in the blanks from that with a cubic formula. You can look it up online. It's so complicated, nobody memorizes it except abstract algebra students. But it is there. You could do it and get exact answers. It's a formula. And same thing for fourth degree, quartic polynomials, we call those. Cubic polynomials are third degree, quartics are fourth. So there's a quartic formula for getting fourth degree polynomials. Pardon me a second. There it is. But Abel's impossibility theorem says amazingly that if you put a fifth degree polynomial or higher, there is no finite expression in terms of algebra, arithmetic powers and roots for finding all the solutions of a fifth degree polynomial equals 0 and hence filling in the blanks. And so kind of quite an interesting result. Abel died pretty young. It's very sad. He got tuberculosis in Paris. You can look at this is Wikipedia here. You can look it up and read all about it. But just before he got his letter, he's going to get a big professorship. He's very famous. He's got, if you ever hear of abelian groups and advanced algebra, it's from Abel, as far as it comes from. So he was quite a good mathematician, died young. But he came up with this beautiful result before he did. And it tells us something that here's the most famous example by another guy named Galois, who extended the theory, that there is no nice formula for this simple fifth degree polynomial equals 0, and hence if you try and fill in the blanks for it, it's not a finite expression in terms of arithmetic powers and roots. And so what are we going to do? If we have a fifth degree denominator or greater, we can hope that it happens to have nice ways to factor, and sometimes you can guess what goes in the blanks like we did with the second degrees, but there is no general formula, so the method falls down there. You use the computer to estimate them real accurately, but maybe you don't get exact results. So it works providing factor the denominator, which always factors, but you may not be able to find exactly what they are in finite time. Kind of interesting result. Even more interesting is Galois' story. Boy, you can relate to him. He was a brilliant mathematician. People think he would have been just amazing, but he lived in the time of the French Revolution. He's a hothead and was going around. He got in a duel with somebody, got shot in the stomach. I think it was a duel over a woman, if I remember right. But anyway, he's got the story here. There's his picture. He died at 20 years old. But people think he would have been a great mathematician. His theory that he got started is now called Galois theory, and the extension of it, graduate students study in graduate school. So it became quite important, his beginning things there. But here's Cauchy, who reviewed some of his work, real famous mathematician. I was going to look down here. There he goes. Says somebody mentioned that Galois found himself in the presence of his supposed uncle and a supposed fiance who provoked the duel. Anyway, but there it is. His last words after he died, like not the same day, but his last words to his brother Alfred: "Don't weep, Alfred. I need all my courage to die at 20." So kind of a sad story. We might have got more interesting stuff from polynomials if he'd lived. All right, so there's some interesting stuff to wake you up, hopefully. Now that you're awake, we got to do the long exams. All right. Here it is, hopefully. Oh. Yeah, isn't that fascinating? I mean, it's like one would never guess that, huh? Yeah, Galois theory is supposedly the elegant way to show that, but I don't know the proof. So, yeah, but if it were easy, it wouldn't be a big deal, I suppose. Um, yeah. So yeah, we could. Yeah. Well, some of you might be. A lot of mathematicians, all the mathematicians take this class too. Now let's see if I can find my paper here again. Got to keep these arranged better. This actually is a real specific example like the one in your book here. And I need all the numbers. I put it here at the beginning. Got part of it. There it is. Okay. Here's my big deal example. This is the hard one. So we'll show you a lot of this stuff here. Suppose I wanted to integrate Again, you can do all this on the calculator fast, but on the test, I'm going to ask you to show me how to integrate this. X cubed minus 19x squared plus 80x plus 100. One of the difficulties with the calculator or the online calculators is they know also Abel's impossibility theorem, and they don't try to factor those things exactly for fifth degree or higher. They may try and guess. I don't know if they're good at guessing yet, but what you have an advantage if you get a 10th degree polynomial at the bottom is you might be a better guesser than the machine and be able to figure out how to factor it down to a product of lower degree polynomials where then you can get the machine to factor it. So there is skill in this as a result. But suppose I wanted to do this one. I need to rewrite this quotient. It turns out that this factors, how do I factor this? Oh, golly. Third degree or higher, like I said, you can use a cubic formula that's known to do it, but it's too hard. Instead, what you do is you try and factor it as x minus blank times either an irreducible quadratic or two more linear factors. And then all times the lead coefficient here, 1. Right? And what goes on the blanks is always what? Remember this from the rational zeros theorem or rational roots theorem? It's called both. What goes in these blanks, blanks, is always, if it's a rational number, it could be a root that's not expressible as a fraction, but it's a plus or minus a factor of the constant term, 100. Does this look familiar? Over a factor of the lead coefficient, 1. Those are the only fractions that can go in there. So if there are fractions, that's what they'll be in there. And so you try guessing all those, and you try putting in, and so there's a lot of answers here. It could be plus or minus 100, plus or minus 25, plus or minus 20. Usually there's not so many choices in the problems I'll give you, but plus or minus 10, plus or minus 5, plus or minus 4. Oh, I forget 50 up there. Plus or minus 50, plus or minus 2, plus or minus 1. That's always 100 factors, and then 1 is just 1. So you have to try all those numbers. What you do is you try the easy ones. Try x equals 1. Put it in here, and you get 1, and you put it in to see if what you want in these blanks is the solutions to x cubed minus 19x squared plus 80x plus 100 equals 0. The solutions to this equals 0, the zeros of the equation we call them, are what goes in the blanks. And so I try x equals 1, I get 1 cubed minus 19 times 1 squared plus 80 times 1 plus 100, and that's positive. That's too big. That's not equal to 0. So I try x equals minus 1, another easy number, and I get minus 1 cubed minus 19 times minus 1 squared plus 80 times minus 1 plus 100, and sure enough, that comes out to be 0. If x equals minus 1 is a 0 of the polynomial, that implies by the theorem from algebra that x minus that number is a factor of the polynomial. So that's another algebra theorem. I told you there's a lot of algebra in this. Better written as x plus 1, right? So x plus 1 divides this polynomial. And what can I do with that? I can now do a long division to find out what the rest of it is. I'll divide the whole polynomial x cubed minus 19x squared plus 80x plus 100 times the thing I know is a factor, or by the thing I know is a factor, x plus 1. Long division, right? Just like we did before, but harder. This time, x plus 1 goes into the lead term here. X goes into x cubed x squared times, so I put x squared. And x squared times x is x cubed. X squared times 1 is x squared, and I have that. Right?